Before we begin, take a moment to imagine the quiet tension of wartime engineers standing before a machine that would challenge everything they thought they knew about armor warfare. What they were about to discover was not just about armor and firepower, but about a philosophy of design that would reshape their understanding of reliability. And later in this story, here on World War Lab, you will see how one single captured vehicle managed to expose an entire technological gap between two industrial giants. Mid-February 1943, Sidi Zid, Tunisia, the captured M4 Sherman tank rolled to a halt in the desert sand, its white American star still faintly visible beneath a roughly painted German cross. Officers from Heavy Panzer Battalion 501 gathered around this prize, notebooks already open in their hands. This single American tank, captured intact and fully operational during the fighting around Sidi Zid, would spark a crisis of confidence among German engineers that would echo throughout their tank development programs for the remainder of the war. The equations of armored warfare were about to be rewritten, not through thicker armor or more powerful guns, but through something the Germans had never truly prioritized: automotive excellence that simply refused to fail. Painted on the hull was the name War Daddy 2. Its serial number was USA 306 7641, built by the Lima Locomotive Works and assigned to Company G of the 1st Armor Regiment, 1st Armored Division. Personnel from a German reconnaissance unit drove the Sherman approximately 350 kilometers across the harsh North African terrain to the port of Sfax, a journey that took 4.5 days. Every kilometer revealed something that contradicted long-held German assumptions about American industrial capabilities. The engine never overheated. The transmission never failed. The final drives delivered consistent performance throughout the entire trip. German tank crews, accustomed to frequent mechanical breakdowns even during short movements, watched with growing unease as his enemy vehicles simply kept working without complaint through terrain and conditions that would have disabled much of their own equipment. At the port, War Daddy 2 was loaded onto a cargo ship bound for Germany. The Army Weapons Office had issued clear and explicit orders. This tank must reach the testing facility at Kummersdorf intact and fully operational. German intelligence had received only fragmentary reports about American tank production, but seeing the physical vehicle transformed abstract statistics into undeniable reality. The Sherman represented mass production on a scale Germany could not match, built with automotive engineering principles Germany had never fully mastered. As the ship steamed northward across the Mediterranean, Wehrmacht engineers prepared testing protocols that would force them to confront uncomfortable truths about their own limitations and the rapidly advancing capabilities of American industry. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. War Daddy 2 rolled off a transport rail car bearing the German designation Zugraf 259 and license plate WH058941. Test engineers had already stenciled armor thickness measurements and angles across every surface of the tank, marking it with precise notations for their comprehensive evaluation program. The German Army Proving Ground at Kummersdorf, located about 25 kilometers south of Berlin, served as the primary testing facility for both German vehicles and captured Allied equipment. Here, meticulous engineers measured, tested, and analyzed everything from track tension to transmission efficiency, documenting their findings in exhaustive technical reports. The Sherman was about to undergo the most thorough automotive examination German engineering could devise. German test engineers conducted the initial inspection using teams of specialists from multiple technical branches. They photographed every component from dozens of angles, measured every clearance with precision instruments, and documented construction methods that appeared almost shockingly simple when compared to German manufacturing practices. The transmission immediately drew the attention of powertrain specialists. Where German tanks relied on straight-cut gears that demanded extremely precise tolerances and frequent maintenance, the Sherman used herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design, standard in American automotive manufacturing since the 1930s, provided exceptional durability while requiring far less precision in machining. German engineers had long considered herringbone gears too difficult to mass-produce given their industrial limitations and workforce training. The Americans, however, had been producing them by the thousands. Testing began with basic automotive trials intended to push every mechanical system under controlled stress. Engineers drove War Daddy 2 through obstacle courses designed to replicate battlefield conditions, measuring fuel consumption, monitoring engine temperatures, and recording transmission behavior under varying loads and terrain. After each trial, components were disassembled to examine wear patterns, searching for signs of stress, inadequate lubrication, or hidden design weaknesses. Again and again, the results contradicted everything German tank doctrine had accepted about the supposed trade-off between performance and reliability. The Sherman performed adequately in every category and excelled in the one area where German tanks consistently failed: operational endurance without maintenance intervention. The powertrain examination revealed fundamental differences in design philosophy between American and German engineering. The Sherman's transmission featured 5 forward gears and 1 reverse, with synchronization in gears 2 through 5. This eliminated the need for double clutching during normal operation and made the tank nearly as easy to drive as a civilian automobile. It required minimal specialized training. German tank crews, in contrast, had to spend significant time mastering complex double-clutching techniques and careful throttle control to avoid damaging their transmissions. The Sherman was designed with the assumption that ordinary soldiers with basic automotive knowledge would operate it, while German designs assumed the constant availability of highly trained specialists. The Continental R975 radial engine installed in this particular Sherman demonstrated remarkable tolerance for varied operating conditions. Engineers observed that it maintained stable performance across temperature ranges that would have caused German engines to overheat or lose power. The cooling system, though simple in design, proved extremely effective. The air filtration system handled desert sand without the frequent clogging that had plagued German tanks in North Africa. Every mechanical system reflected a design philosophy that prioritized practical functionality over theoretical perfection, emphasizing reliability and ease of maintenance above all else. June 6th and 7th, 1943, at the Hiller-Sleben Artillery Range, Reich Minister Albert Speer arrived to preside over a major armaments conference attended by leading figures from the German weapons industry and senior Wehrmacht officers. The demonstration program included hill climbing trials that directly compared German tanks with captured Allied vehicles. War Daddy 2 stood alongside the newest German designs, including a Panther Aus, D fresh from production line, and a Ferdinand tank destroyer that represented the pinnacle of Germany's armored fighting vehicle technology. Speer, responsible for armament production and personally accountable to Hitler for results, needed a clear understanding of what American industry was capable of producing and how German designs truly measured up against enemy equipment. What the demonstration revealed would offer answers that neither Speer nor German tank designers were prepared to fully accept. The Sherman climbed the test slope smoothly and without hesitation. Its manual transmission, with 5 forward gears synchronized from 2nd through 5th, shifted cleanly and effortlessly. The engine delivered steady, uninterrupted power throughout the ascent. The driver handled the vehicle with calm confidence, demonstrating the ease of operation that would become one of the Sherman's defining characteristics. The Panther followed, its far more powerful 700 horsepower Maybach HL230 engine, allowing it to match the Sherman's performance, but only barely, and only with considerably more effort and strain. The Ferdinand, enormously heavy at 65 tons and technically ambitious with an electric transmission system, stalled partway up the incline. Speer watched as recovery crews struggled to restart the vehicle, the failure unfolding in front of dozens of senior officers and industrial leaders. The embarrassment was unmistakable. Years later, in his memoirs, Speer would reflect on the capabilities of the Sherman he had observed during his inspection tour of Italy in October 1944. He wrote that reports on the cross-country mobility of the Sherman had been extremely favorable, noting that it climbed mountainous terrain German tank experts had believed to be inaccessible to armored vehicles. He attributed this to the Sherman's powerful engine in proportion to its weight, which gave it superior mobility both on level ground and in difficult terrain. The 26th Panzer Division had specifically reported this advantage in its own assessments. Observations coming from Germany's armaments minister carried immense weight within Wehrmacht circles. A carefully worded public assessment appeared in the newspaper Das Reich on June 27, 1943. The article described the Sherman as one of the special achievements of North American laboratories and praised it as a highly commendable product of the North American steel industry. It noted that the first aspects to attract attention were its serial production methods and fulfillment of what were described as the almost arrogant standards of the North American automobile industry. The article also mentioned the gyro-stabilized gun as the first practical attempt of its kind anywhere in the world, acknowledging American innovation in this field. These statements, written cautiously to avoid sounding defeatist, concealed the deep concern spreading through German engineering departments. American tanks were not merely adequate. They were fundamentally better engineered for sustained operations in real battlefield conditions. Back at Kummersdorf, systematic testing continued through the summer and into the autumn of 1943. Engineers measured the Sherman's operational range through extended trials that pushed the vehicle to its mechanical limits. They documented operational distances exceeding 2,000 kilometers before major maintenance was required, roughly 4 times what early model Panthers could achieve under field conditions. They measured transmission efficiency that surpassed any German tank, with power losses through the drivetrain significantly lower than comparable German systems. The synchronized manual transmission drew continued attention as it made gear changes smooth and simple, eliminating the need for double clutching or careful engine speed matching that German transmissions demanded. The final drives presented another revelation that directly challenged German engineering assumptions. German Panther tanks used final drive systems inherited from the Tiger design, configurations that proved highly vulnerable under stress. They relied on straight-cut gears housed in casings that were inadequate for the loads imposed by a 45-ton vehicle. German mechanics in North Africa and on the Eastern Front had repeatedly reported final drive failures, forcing Panthers to be abandoned after relatively short movements, sometimes in less than 100 kilometers of travel. The Sherman's final drives, built using the same herringbone gear principles as its transmission, rarely failed, even under sustained combat conditions that would quickly destroy German components. Decades later, restoration projects would uncover Sherman final drives that required no mechanical rebuilding after years of storage, a testament to design margins that exceeded immediate operation requirements by substantial factors. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated throughout Wehrmacht technical branches. These documents, intended for senior officers and officials within the armaments ministry, painted a deeply sobering picture. The Sherman demonstrated a level of maturity in American automotive engineering that Germany fundamentally lacked. Despite its strong theoretical knowledge and scientific expertise, American mass production techniques allowed tolerances that German precision manufacturing would have considered careless, yet these methods resulted in vehicles that were more reliable and more effective under real field conditions. Interchangeable parts meant that field repairs could be carried out with basic tools and minimal specialized training. While German vehicles often required factory-level precision and specialized equipment for many repairs, the American design philosophy centered on keeping vehicles operational at all times rather than pursuing theoretical maximum performance that looked impressive on paper but could not be sustained in combat. Internal German engineering assessments went even further, documenting American industrial advantages that extended beyond simple production volume. American automotive engineering reflected decades of civilian industry experience that Germany had never developed on a comparable scale. Before the war, automobile ownership in the United States was widespread, with cars common among ordinary citizens across nearly all economic classes. In Germany, civilian automotive experience was far more limited, with cars remaining luxury items largely restricted to the wealthy and the party elite. The Volkswagen program promised to German workers since 1934 had delivered fewer than 1,000 civilian vehicles by 1939, highlighting the vast difference in industrial foundation that now manifested itself so clearly on the battlefield. This enormous gap in automotive industry maturity translated directly into two completely different tank design philosophies. The Americans built tanks that could be maintained by mechanics who already had civilian automotive experience, using skills they had learned long before entering the military. The Germans, by contrast, built tanks that demanded specialist training and constant attention from personnel who required years of specific technical education. As field reports accumulated through late 1943 and early 1944, the comparison in reliability became impossible to ignore. Panther tanks required strict operational limitations simply to avoid mechanical failures that would leave them immobilized. Drivers received explicit instructions not to change gears frequently because excessive shifting damaged the transmission. Third gear, in particular, failed so often that field manuals warned against using it unless absolutely necessary. Panthers were not allowed to turn while reversing, as doing so could destroy the transmission. Pivot turns were only possible when ground resistance was equal on both tracks, severely restricting tactical flexibility. Even foreign objects entering the running gear could jam the drive sprocket, forcing hours of maintenance work to clear. All of these issues existed despite Panthers being built in specialized tank factories by skilled workers using the best materials Germany could provide. The Sherman stood in complete contrast. It had been designed by automotive engineers at General Motors, Ford, and Chrysler, using mass production principles developed through decades of civilian vehicle manufacturing. The tank incorporated commercial automotive components wherever possible, taking advantage of established supply chains and proven manufacturing expertise. The transmission alone was produced by multiple companies, including Caterpillar Tractor, Buick, and the Ford Motor Company, all building to identical specifications. Parts were fully interchangeable and could be mixed freely without adjustment. This level of standardization was routine in the American automotive industry, but remained largely theoretical in German tank production, where each manufacturer introduced subtle differences that prevented true interchangeability. Additional captured Shermans arrived at Kummersdorf throughout 1943 and 1944, including vehicles taken from British units in Italy and from Soviet forces on the Eastern Front. Each tank underwent the same rigorous testing process, gradually building a comprehensive database that documented American tank capabilities across different variants and production periods. Some of the British Shermans have been refitted with a powerful 17-pounder anti-tank gun, creating the Firefly variant that addressed the Sherman's main weakness in firepower. German engineers studied these modified tanks with particular interest, noting how the Sherman's large turret ring allowed the significantly larger gun to be installed with minimal modification. The Firefly demonstrated growth potential built into the original design, something German engineers had not considered when specifying their own vehicles. The Panther, rushed into production to counter the Soviet T-34, lacked any real capacity for significant armament upgrades. Installing a larger gun would have required a complete redesign of both the turret and much of the vehicle itself. The Sherman, by comparison, had been engineered with future expansion in mind. The automotive testing program expanded to include reliability trials specifically designed to replicate battlefield conditions. Engineers drove Shermans through hundreds of kilometers of cross-country movement, carefully recording every mechanical incident, maintenance requirement, and component failure. These results were then compared with field reports from Panther and Tiger units operating on the Eastern Front and in Italy. The numbers told a clear and unambiguous story about comparative reliability. Panther operational readiness averaged below 40% throughout most of 1943, with some units reporting catastrophic rates as low as 20 to 25%. Individual Panther battalions recorded periods when fewer than 1 in 5 tanks were actually capable of combat operations. By comparison, Sherman tanks consistently maintain far higher operational availability across all theaters of war. German field reports documented Panther reliability problems in devastating detail. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness, with mechanical failures eliminating more tanks than enemy fire. By December 1943, readiness had improved to just 37%. Reports from February 1944 again showed 37% operational. April 1944 reached 50%, and May 1944 finally climbed to 78%. These figures represented percentage of Panthers actually capable of combat on any given day, with the remainder broken down awaiting parts or undergoing repair. The progression showed gradual improvement as design flaws were addressed, but even the best Panther readiness rates never matched what Shermans had achieved from their earliest production. By December 1943, the pattern had become undeniable to any objective observer examining the data. The engine lifespan for the Sherman diesel variant exceeded 3,000 kilometers under proper maintenance. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems. German reports from March 1944 described improved Panther engines achieving a service life of 700 to 1,000 kilometers and presented this as a success. In reality, this only brought Panther engines to roughly one-third of the endurance achieved by Sherman diesel engines. Sherman transmissions required minimal maintenance between overhauls, with synchronized gears that reduced the chance of driver error causing damage. Panther transmissions demanded constant attention and frequent repair. Third gear failures were so common that drivers learned to skip directly from second to fourth gear to avoid using the problematic ratio. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within just 100 to 200 kilometers of use. Field reports from German units that operated captured Shermans reinforced the testing data from Kummersdorf with real-world experience. German mechanized units, desperate for reliable vehicles as their own tank strength deteriorated, eagerly employed any intact American tanks they could obtain. Unlike captured Soviet T-34 tanks, which require extensive modification before German use, Shermans entered German service without alteration. They required no modification because they already worked as intended. They functioned correctly by design, without fundamental flaws that needed to be corrected. German tank crews who had endured repeated mechanical failures in their own vehicles found the Sherman's reliability astonishing, and they commented on it frequently in letters and official reports. Reports from Panzer regiments emphasized that Sherman crews were able to focus on tactics and combat effectiveness, while Panther and Tiger crews were constantly preoccupied with whether they would even reach the battlefield without a breakdown, or whether their mission would be cut short by mechanical failure that immobilized their vehicle. In January 1945, during Operation Nordwind, the 10th SS Panzer Division captured 12 M4A3 Shermans at Hattenheim. These tanks had belonged to the American 43rd Tank Battalion and were taken intact after their crews abandoned them during the German assault. The 12 Shermans were organized into the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war. They were used primarily as reconnaissance vehicles and mobile reserves, roles that demanded long periods of sustained movement without maintenance stops and absolute mechanical dependability. German commanders recognized what the testing at Kummersdorf had already proven years earlier. American tanks could be trusted to function when they were needed. This reliability, even more than firepower or armor protection, determined real tactical usefulness in the final months of the war. A Sherman arriving on the battlefield with a functioning gun was infinitely more valuable than a Panther with superior firepower that had broken down 20 kilometers behind the lines. January 1944 brought expanded testing programs as Wehrmacht forces retreated across multiple fronts and additional captured equipment arrived at Kummersdorf. Engineers examined the M4A1 equipped with the Continental R975 radial engine, documenting its performance characteristics and comparing it to other Sherman variants. They tested the M4A2 powered by the twin General Motors 6046 diesel engines, noting its superior fuel efficiency and distinct operating behavior. They evaluated the M4A3 fitted with a Ford GAA V8 gasoline engine, which American crews widely regarded as the best Sherman power plant. Every variant demonstrated the same fundamental quality: exceptional automotive reliability derived from sound engineering principles and disciplined manufacturing processes. The consistency across these variants deeply impressed German engineers, who were accustomed to significant quality differences between manufacturers producing vehicles that were nominally identical. The diesel-powered M4A2 was particularly impressive to the engineers at Kummersdorf. Soviet forces had received approximately 4,102 of these tanks through Lend-Lease, and substantial numbers fell into German hands during retreats on the Eastern Front. The twin GM 6046 diesel engine delivered performance equal to any Sherman variant while consuming far less fuel than gasoline engines, a critical advantage as German fuel supplies became increasingly scarce. German designers had experimented with diesel tank engines, but abandoned the concept because of manufacturing difficulties and the complexity of fuel injection systems. American industry, by contrast, produced diesel-powered Shermans alongside gasoline versions without disrupting production schedules, demonstrating a level of manufacturing flexibility and technical sophistication that German industry never achieved under wartime conditions. In March 1944, reports arrived from General Heinz Guderian, Inspector General of Panzer Troops, noting in official communications that improvements to Panther reliability had finally reached what he described as acceptable standards. Engine life had increased to between 700 and 1,000 kilometers, and final drive problems had been largely resolved through design changes and improved manufacturing processes. These developments were presented as major successes in German military communications. In reality, they merely brought Panther reliability up to the level that the Sherman had achieved from its initial production in 1942. The German army celebrated reaching standards that American tanks had surpassed from the very beginning, a stark illustration of how far behind German armored vehicle development had fallen. The comparison became even more painful as German tank production struggled under growing resource shortages and the impact of Allied strategic bombing. Allied bombing campaigns increasingly targeted critical bottlenecks in Panther and Tiger production with devastating effectiveness. The Maybach engine plant in Friedrichshafen suffered catastrophic damage during a Royal Air Force Bomber Command raid on the night of April 27 to 28, 1944. The attack involved 322 aircraft and is described in the Imperial War Museum archives as the most damaging single raid against German tank production during the entire war. The bombing also destroyed the ZF gearbox factory located adjacent to the engine plant. Production of tank engines and transmissions was brought to a complete halt for 6 months. When production finally resumed in November 1944, quality control had deteriorated severely. Slave labor, increasingly used in German tank factories as skilled German workers were drafted into military service, introduced widespread and deliberate sabotage. Cigarette filters were pushed into oil passages. Gaskets were installed incorrectly. Components were assembled without proper clearances. These issues never affected Sherman production, which took place safely in American factories far from any combat zone and staffed by workers who were motivated, well-paid, and operating under stable conditions. The fundamental difference between American and German tank production lay not in engineering knowledge, but in industrial capability and design philosophy. German engineers understood automotive principles as well as their American counterparts and possessed immense theoretical knowledge and scientific expertise. What they lacked was consistent application of those principles to tank design. Instead, German tank development prioritized other factors. German vehicles emphasized impressive performance characteristics on paper, often at the cost of real-world reliability. The Panther's powerful 75mm KWK-42 gun and thick frontal armor were achieved by pushing its powertrain to the absolute limit, creating a system that could not reliably support the vehicle's 45-ton weight. The Tigers' formidable battlefield performance demanded extremely complex maintenance procedures and constant attention from highly trained specialists. These trade-offs might have been acceptable if German industry had been capable of producing sufficient numbers of vehicles and enough spare parts to keep them operational. It was not, especially as Allied bombing intensified and raw material shortages worsened, leaving German armor forces increasingly unable to sustain the machines that looked so formidable on paper but proved so fragile in reality. The worsening situation only highlighted the contrast between the two industrial systems. American engineers, trained in automotive mass production through decades of civilian industry experience, designed tanks that could be manufactured by the tens of thousands and maintained by mechanics with only basic training, using skills learned in civilian life. The Sherman powertrain relied on components already proven in commercial service, with design principles taken directly from automobile and truck manufacturing. Its electrical system even included a backup generator capable of powering turret traverse when the main engine was shut down, a feature that German designers considered an unnecessary luxury, yet one that proved invaluable in combat. German tank crews could only imagine such conveniences, especially those who had experienced their turret traverse failing when an engine stalled on a slope. These elements never appeared in German technical priorities, because German designers focused far more on armor thickness and gun power than on operational convenience and reliability. By the spring of 1944, Wehrmacht units on all fronts reported growing mechanical problems as manufacturing quality declined and spare parts became increasingly scarce. Panthers often had to be transported by rail for movements exceeding 100 kilometers because their final drives could not survive sustained road marches. Field commands issued explicit orders restricting Panther movements in order to preserve the vehicles for actual combat, instead of losing them to mechanical failures during approach marches. Even the Burge Panther recovery vehicle, built on a Panther chassis to recover disabled Panthers, suffered from the same reliability problems as the tanks it was meant to rescue. German commanders were forced to confront the grim reality that mechanical failures were destroying more tanks than enemy action, with some units reporting that as many as 70% of their losses were due to breakdowns rather than combat damage. Meanwhile, Sherman production continued at levels German industry could never hope to match. American factories produced 49,324 Sherman tanks during the war, more than the total production of all German tanks of all types combined. British Commonwealth forces received thousands through Lend-Lease. The Soviet Union received over 4,000 diesel-powered variants. Chinese forces in Burma used Shermans with devastating effect against Japanese armor that was technologically inferior to both American and German designs. In every theater where Sherman served, the same conclusion emerged. Properly maintained Shermans kept running under conditions that would disable or destroy German tanks. German tank crews who captured and operated Shermans universally praised their automotive excellence in letters, reports, and post-war interviews. Reports from the Eastern Front noted that German mechanics found even the complex Chrysler A57 multibank engine, with its 5 separate engine blocks, easier to troubleshoot than German tank engines that required specialized knowledge and equipment. The Ford GAA V8, praised by Allied crews for its reliability and power output, seemed remarkably dependable to German mechanics accustomed to Maybach engines that required constant adjustment of valve clearances, ignition timing, and carburetor settings. The General Motors twin diesel, which the U.S. Army itself had considered less reliable than gasoline engines and therefore relegated mostly to Lend-Lease production, far exceeded performance and reliability of any diesel engine German industry had produced for tank use. The Sherman's generous design margins provided yet another advantage that German engineers eventually came to appreciate. The basic transmission and final drive components originally specified for the 30-ton M4 with a 400 horsepower engine required no major modification to handle the 42-ton M4 3E2 jumbo assault tank, which dramatically increased armor protection. The same components that powered the standard Sherman were able to transmit 650 horsepower from experimental engines without failure or reinforcement. German engineers typically viewed such overbuilding as wasteful, believing it represented unnecessary excess capacity that increased costs and consumed scarce materials without immediate benefit. American engineers understood that these margins created growth potential for future upgrades and ensured battlefield reliability, making the additional investment worthwhile over the vehicle's entire service life. By the summer of 1944, German tank commanders facing the Allied invasion in Normandy understood that their disadvantages went far beyond performance of individual tanks. American artillery superiority, devastating close air support, and overwhelming logistical capacity combined to overwhelm German forces, regardless of technical specifications or tactical skill. But the Sherman's reliability meant that American armored units could sustain continuous operations in a way German panzer divisions simply could not. American tank battalions could attack, maintain combat operations, conduct rapid pursuits, and immediately prepare for the next mission without long maintenance pauses. German panzer divisions had to carefully conserve their limited number of operational vehicles, knowing that every movement consumed what little remaining component life they had and brought mechanical failure closer. Operational availability, not raw specifications, determined which force could maintain offensive pressure and which was forced to ration its shrinking combat power. German use of captured Shermans in combat operations provided the final confirmation of American automotive superiority from the German perspective. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, attempted to acquire captured American vehicles to disguise its movements. German planners wanted Shermans in particular because of their reputation for reliability. In the end, the brigade received only 2 Shermans, and only one was serviceable enough for operations. Even that one never actually saw combat, because massive traffic jams prevented the infiltration plan from achieving its objectives. In a mission that required vehicles to operate deep behind enemy lines without breakdowns and far from any support, only American equipment offered a reasonable chance of success. German tanks, even when fully operational, simply could not guarantee the same level of dependable performance. To provide the sustained performance such missions demanded, January 23, 1945, brought the final official admission of German automotive failure. A meeting of the Panzer Commission produced a report documenting catastrophic final drive breakdowns across all German tank types. The findings were devastating. Before the 1945 Eastern Offensive even began, there were 500 effective final drives in the Panzer IV, 370 in the Panther, and roughly 100 in the Tiger. In addition, about 200 failures had already been reported in the Hetzer tank destroyer, which was based on the Czech 38-ton chassis. General Wolfgang Nomail, a general lieutenant and chief of staff of the Inspector General of Panzer Troops serving under Guderian, described the operational impact in brutally honest terms. Under such circumstances, orderly use of tanks was simply impossible. Troops lost confidence in their vehicles, and in some situations entire tanks were abandoned solely because of final drive problems, out of fear that they would become stranded and captured. German tanks, designed to intimidate through impressive technical specifications, failed in the most basic requirement of any armored vehicle: mechanical reliability sufficient to reach the battlefield and complete a mission. The Kummersdorf testing facility began preparations for evacuation in early 1945 as Soviet forces advanced relentlessly toward Berlin. Engineers worked frantically to pack testing data and ship documentation to facilities farther west, hoping to preserve years of technical intelligence for post-war analysis. Some of the captured tanks, including at least 2 Shermans, were pressed into improvised combat service with German units desperately defending the approaches to the capital. These vehicles fought alongside German designs in the final battles, providing one last comparison under real combat conditions. The Shermans continued operating until they were destroyed by enemy fire or abandoned only when fuel supplies ran out. German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even crews already accustomed to poor reliability. The story of War Daddy 2 and the dozens of other Shermans tested at Kummersdorf represents one of the most striking industrial contrasts of the Second World War. German engineers, working inside a system that valued theoretical perfection over practical utility, produced tanks that looked formidable on paper but failed in sustained field operations. American engineers, applying decades of automotive manufacturing experience to military needs, produced tanks that were often less sophisticated in theory, but worked reliably under conditions that defeated German equipment. In armored warfare, as in most forms of combat, the weapon that functions when needed is superior to the weapon that might be theoretically better if it could actually reach the battlefield and complete its mission. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had already revealed. Systematic examination of destroyed German tanks showed mechanical failures to be as common a cause of loss as enemy fire. Final drives shattered by stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded designers to the critical importance of reliability and maintainability. They built tanks that no conscript mechanic could maintain without extensive specialized training, powered by engines that demanded constant expert attention, supported by a logistics system that collapsed under the burden of supplying countless unique parts to scattered units. The lessons learned through testing at Kummersdorf directly influenced German tank design thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development. The Leopard 1 incorporated many of the same design philosophies that had made the Sherman successful: a robust powertrain with substantial design margins, easy maintenance requiring minimal specialized tools, standardized components that enabled rapid field repairs, and growth potential that allowed future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The captured Shermans at Kummersdorf, including War Daddy 2 with its distinctive name still painted on the hull, represented far more than enemy equipment brought home for technical evaluation. They were tangible proof that industrial maturity and sound engineering principles rooted in practical experience mattered more than theoretical innovation pursued without regard for manufacturing reality. German tank designers believed superior technology could overcome material shortages and numerical inferiority. They were wrong. American tank designers built reliable vehicles because they understood, through long industrial experience, that logistics, maintenance capability, and sustained operational availability determine victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between the Sherman and German tanks influenced not only tactical armor warfare, but also shaped a broader understanding of how military industrial capacity determined success in modern conflict. Germany entered World War II with technical advantages in many weapon systems, possessing scientific knowledge and engineering expertise that often surpassed its opponents. What it lacked was the industrial depth and manufacturing sophistication required to sustain those advantages through mass production while fighting on multiple fronts. The United States entered the war with weapons that were, in many respects, less technically sophisticated, but it possessed the industrial capacity to manufacture them in overwhelming numbers, while continuously improving quality, reliability, and performance through feedback from combat experience. This industrial approach, perfectly embodied in the design and production of the Sherman tank, proved far more effective than German technical sophistication applied to small-scale manufacturing. The United States produced nearly as many Shermans as Germany produced tanks of all types combined, while at the same time manufacturing vast quantities of every other weapon system. supplying its allies through Lend-Lease, and maintaining the highest standard of living among all the nations at war. This economic performance, something Germany could not match even before strategic bombing reached its full intensity, decided the outcome of the war as surely as any battlefield victory. The mathematics were simple and brutally clear when examined objectively. A Sherman armed with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before ever engaging the enemy or required 3 days of maintenance for every single day of operation. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with only 40% operational strength simply could not even attempt. Reliability was not a convenience or a secondary factor. It was a foundation of operational effectiveness, determining whether armored units could carry out their assigned missions at all. German tanks consistently failed this fundamental test throughout the war. American tanks consistently passed it. Testing at Kummersdorf had proven this beyond any reasonable doubt by mid-1943. Even as German commanders continued deploying Panthers and Tigers that looked terrifying and possessed impressive specifications, yet could not be depended upon to function when they were needed most. The Sherman tank did not win World War II through technical superiority in firepower or armor thickness. It won through industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance. German engineers at Kummersdorf understood this by mid-1943 based on their exhaustive testing. They wrote detailed reports documenting their findings. They tested their conclusions repeatedly with scientific rigor. They reached the correct understanding of American advantages. But understanding a problem and solving it are two very different challenges. German industry lacked the capacity to completely retool its production around reliability-first principles while simultaneously fighting a losing war on multiple fronts against enemies with vastly superior resources. American industry, by contrast, had built reliability into its civilian automotive sector over decades of commercial competition and simply extended those mature principles to military production with remarkable success. War Daddy 2, the single Sherman captured in Tunisia and tested exhaustively at Kummersdorf for months, told the entire story through a mechanical consistency and unshakable performance. Every kilometer of travel, without failure, was proof that German tank design had taken a fundamentally wrong path by prioritizing specifications over reliability. Every test that demonstrated American automotive excellence was evidence that industrial maturity and practical manufacturing experience mattered more than theoretical performance calculations. Every comparison between Sherman and German tank reliability showed that the Americans had already solved problems that German engineers did not even realize they needed to solve. The tank itself was unremarkable in many ways, just one machine among more than 49,000 produced. But what it represented was devastating to German confidence. It was proof that Germany had already lost the industrial war even as the fighting continued, and that American productive capacity could not be matched, regardless of German technical sophistication or tactical skill.